Hi all. Here is our last video for the biochem topic. Well, SL, but none of you guys are doing HL. And we're looking at biochemistry and the environment. So as always, starting with our points, we're going to define what xenobiotics are, what biodegradable. We're going to talk about host-guest chemistry and enzymes. We're going to talk about biomagnification and green chemistry. We're going to link xenobiotics to things like sewage treatment plants. We're going to talk about starch in the context of biodegradable plastics. And we're going to talk about the removal of, I think I want to talk about maybe heavy metals, I'm not sure. And we're going to talk about green chemistry. Okay, so when we talk about host-guest chemistry, something that's important is that we're talking about non-covalent interactions. So we're talking about LDF interactions between the host and the guest. And we're also talking about dipole attractions and hydrogen bonds. Okay. So the first type of environmental contaminant that we're going to look at are xenobiotics. So xeno comes from the same word origin as xenophobia. Now, most people think of xenophobia as being racism, but xeno literally means outside. So xenophobia is a fear of people from outside or another place. A xenobiotic is something found in nature that's from the outside, that doesn't belong there. Now, the most famous xenobiotic that we know a lot more about now are antibiotics. So, for a range of reasons, from the fact that antibiotics aren't heavily modified by our digestive system when we do excrete them when you're on antibiotics, to the fact that antibiotics are now used in farming, the concentration of antibiotics is increasing in the environment. So antibiotics come from livestock and also human use. So even though antibiotics are such as penicillin, those are actually derived from bacteria. They are something that can be naturally produced, like our bread molds back when it was originally extracted. Antibiotics, because they don't naturally occur in a bunch of these in nature, other than those couple of compounds, couple of organisms that make it, the concentration of antibiotics is increasing in the environment. And then bio people, I'm sure you've spoken about this, that increased concentration of antibiotics in the environment is having a really major effect on resistant bacteria, on the development of resistant So an antibiotic, by definition, when you break down the word, means against living things. So antibiotics are used to kill bacteria. So if you have COVID-19, do not ask for an antibiotic. COVID-19 is a virus, an antibiotic will do nothing. So because of the increase of antibiotics in the environment, there are bacteria that are resisting those antibiotics. So, for example, there is a bacteria called MRSA, M-R-S-A, multi-resistant Staphylococcus aureus, However, in terms of something that could just outright kill numbers of bacteria, there are resistant forms of TB. Now, TB, tuberculosis, isn't something that we worry about in Australia. It's something that is a disease of like my grandparents and my great-grandparents' generations. But in other parts of the world, TB is still a massive killer just in terms of numbers. So an example of a xenobiotic are the increasing concentrations of antibiotics in the environment. And one of its big impacts is on the development of resistant bacteria. So there are some other xenobiotics. So one is dioxins, and one of the others that you might have heard of are heavy metals. Quick tip, if you are going to Google heavy metals in the environment, write minus music, just it'll cut down on your Google searches. So heavy metals are things like lead, mercury, even gold. So lead and mercury are the two ones that we hear of most frequently. And because these aren't things that we generally have in our diets, our bodies have not evolved ways for us to excrete them. So these tend to, on exposure, build up. So they tend to build up in the organism. So lead can have a variety of different effects, some of which are really quite scary, because lead can actually substitute for calcium in bones, which makes it really hard for drugs to actually work to get it out of our bodies, because if they're locked up in the bones in a phosphate form, any drug that's designed to remove it from the bloodstream isn't going to work. Mercury also has some pretty gnarly neurotoxic. So I think I've mentioned the old phrase mad as a hatter, or if you've ever read Alice in Wonderland. The hatter is mad because mercury was actually used as a way of setting felt. So felt is basically wool that's been all jumbled up, and it actually used to be treated with mercury to make it set, I believe. I don't make felt. But in order to shape the brims of hats, hatters used to actually grip the brim of the hat in their jaw and then shape it with both hands so it was symmetrical. And by doing that, they were ingesting mercury. Now, a small amount of mercury isn't terribly neurotoxic. We've probably all got some mercury in our body because most of us eat fish or seafood. But in high concentrations, mercury can actually be very neurotoxic. So the hatters that had massive exposures, it caused death of nerve cells, and it caused them to become mentally unwell. So on the last slide, I mentioned dioxins. I've got over here an image of 3 of the main environmental contaminant dioxins. They're called dioxin because of the 2 oxygens that are in the middle. Now, dioxins are really nasty. They cause birth defects, and I believe they're also carcinogenic. And they're formed by the burning of plastic. So when you burn plastic, and you know that nasty smell that burning plastic makes, some of that is from gaseous hydrogen chloride. So the gaseous form of hydrochloric acid before you've dissolved it, basically. That burning plastic, some of that nastiness is from these dioxins. So if you're going to burn plastic, which I don't recommend, it has to be at a super high temperature. Because if you burn it at a low temperature, you end up making these dioxins. And these dioxins, because they're not naturally occurring compounds, there aren't really that many bacteria out there that are able to break these guys down. They tend to persist in the environment. So when we're looking at environmental contaminants, regardless of whatever it is, there's a couple of things we need to think about. We need to think about how damaging or how harmful is that, sorry, how damaging or how harmful is that xenobiotic, but also how persistent is it? So looking at heavy metals, for example, we are literally talking about metal ions. Short of nuclear reactions, we can't get rid of them. We can't eliminate or break down that contaminant. With something like dioxins, they are organic compounds, so we can break them down, I believe, but it's not a simple process. So let's talk about biodegradable plastics. Traditional plastics, they are hydrocarbons, and they're polymers, so based off ethene, which means they're derived from oil, which I'm guessing we've all seen enough Attenborough docos to tell us that that's not the best idea. And because they are effectively an unnatural substance, bacteria have a really tough time breaking it down. Now, I'm just going to switch colours quickly because there are some bacteria that have been found that have evolved to be able to break down plastics, like traditional ethene polymer plastics. So there are some bacteria that have worked out how to do that, but it's not many. So biodegradable plastics are made up of starch molecules with those glycosidic linkages that we talked about back in the carbohydrates section. Now, what that does is, because they're glycosidic, there are bacteria that know how to break those down. That is a natural shape of a molecule as far as bacteria are concerned. So this comes from a renewable source. So you can actually make plastics at home using potato starch. I had a kid do an EE on it a few years back. So you can make plastics using starch. So we can grow the plants that are then turned into the plastic that are then biodegraded back into carbon dioxide and water. So, and also because of, if you remember back to our shape of our glucose molecule, remember it's got all of those hydroxyl groups around it? That then means that once it gets broken down into smaller pieces, it can be soluble in water. However, this has some downsides to it. So yes, it can be broken down by water, but it can also form methane. If it's done in an anaerobic environment, it produces methane, which is a much more potent greenhouse gas than carbon dioxide is. It's renewable, and I said this to the others during their video on biodiesels, but going from making plastics out of oil to making plastics out of starch doesn't solve the problem of us using plastic. It doesn't actually motivate any behaviour change. Sorry, just remembered something. Yes, it can be broken down by bacteria, but this can be slow. So there are some really solid positives to transitioning from using traditional plastics to starch plastics. However, there are some downsides. Methane is the big one that a lot of people talk about, but I think the one that's going to come back and bite us in the arse in 30 odd years is going to be the fact that it isn't actually changing our behaviours. It isn't changing, how we shop, how we store things. Okay. So enzymes can be used in two main different ways as green cleaning products. One of the main ways is for oil spills. So this is technically called bioremediation. So remediation is fixing, and then bio is using a biological agent. So in the case of oil spills, we can actually, once the oil has been dispersed, distribute enzymes to break down the oil. So I think they were used after Deepwater Horizon in the Gulf of Mexico. So enzymes are added to break down oil. Now, one of the main places where this comes from is actually detergents. So if you look at the laundry detergent that you've got at home, it might be like enzyme power, powered with natural enzymes, blah, blah, blah. And that's because enzymes can be used in detergents in order to break down stains. So when you think about it, a lot of the stains that we get on our clothing are derived from natural products. So tomato juice, blood, sweat, all of those are natural products, which means that we can find a natural solution to help clean them up. So enzyme detergents are a really powerful way that enzymes can be used. And their main benefit in terms of the environment is that one of the ways that you can get stains out of clothes is basically cooking them in super hot water. Now, obviously, if we're using enzymes, if you remember our activity curves, that's at super high temperatures, the enzymes aren't going to work. So what enzyme-powered detergents allow us to do is actually do our washing at a lower temperature, which is going to decrease the energy demand. So washing something in cold water doesn't take as much energy as washing the same thing in hot water. All right. So host chemistry is a really interesting area, and it's what is called supra, S-U-P-R-A, molecular. So host gas chemistry works on supramolecular interactions. So supra comes from the same sort of origin as super. It means above or beyond. Molecular means, well, you're chemistry people, so I'm guessing you've got that one. But host gas chemistry isn't about the interaction on like a covalent level of a molecule. We are talking about the interactions between two separate molecules. So, sorry, host gas chemistry can be used to remove pollutants from the environment by binding through LDFs, through dipole interactions, and ionic. Basically, not covalent. So host gas chemistry can be used to remove a number of things from the environment, basically, and think about it like a substrate and an enzyme. You've got to match up a negatively charged portion of your host with a positively charged portion of your guest, or vice versa. You've got to match up a non-polar section of your host with a non-polar section of your guest, and that allows a really tight bind between the host and the guest. And that's what allows us to actually design compounds that can remove these guest molecules. So it is the guest molecule that is our xenobiotic. And it's those interactions that allow us to remove that xenobiotic from the environment that it's in, whether that's like a chelating agent being put through a human's body, whether it's making sure that a particular type of waste doesn't have a particular isotope before we put it in storage. It's those non-covalent interactions that allow us to remove some xenobiotics from the environment. So earlier I talked about one of the ways that these xenobiotics, their danger can be measured by their persistence, how long they stick around for. Biomagnification, and again, it's something that you might have talked about it in biology, it's about how the xenobiotic persists in the environment and moves up the food chain. For example, if there are plankton that have a very small amount of mercury in them, you've then got one fish that eats a whole stack of those, did I say algae or plankton? I don't know. So I've then got a fish that eats a whole stack of that. So the mercury builds up in that fish just because one tiny little organism had a small amount of mercury, but then you've got the fish that's eating a whole stack. Then let's say that I eat fish once a week. That toxin would then build up in my body. So biomagnification is the increase in concentration of a pollutant as you move up the food chain. So let me just write that one down so we've got it. So this is particularly damaging for us because we're humans and we're disgusting and we'll eat just about everything. So, but one of the biggest examples is actually DDT. So DDT is a compound that you might have heard of. It used to be like a common component in like supermarket bought bug spray. It is a pesticide, and it's particularly good at killing mosquitoes. So, and the reason that we used it so widely was to actually decrease malaria. So to decrease the number of mozzies that were out there, to decrease the risk of transmission of malaria. Now, one of the issues with DDT, and that's its chemical structure down in the corner, one of the issues with it is that it is persistent and it biomagnifies. So it does an awesome job at killing mosquitoes. It's super, super effective. But one of the issues is it does build up in the food chain. So one of the side effects on the environment of the use of DDT was a whole bunch of birds went extinct. Or were threatened. Because somehow, and you don't need to know the details of this, DDT interferes with shell formation in eggs. So if you've got a clutch of 4 eggs, 3 of them might hatch, of which 2 might survive to adulthood. However, if those shells are thinner, those shells are more fragile and they are less likely to hatch a bird. Sorry, just a last note on DDT. DDT is an awful chemical. It's led to massive problems with food chains. It particularly, because of the way biomagnification works, it particularly affects birds of prey, so those animals up the top of the food chain. But DDT is still not banned in all countries. It's banned in a lot, but it isn't banned in all. So in countries where malaria is still a real danger to people's lives, DDT is still used in order to eliminate the mosquitoes. It is still incredibly effective at that. Okay, I think I've said enough about DDT. Happy to take other questions on it, but let's move on. Okay, so green chemistry, I might actually start with, sorry, I might actually start with atom economy. So atom economy is just a pretty simple formula. It's the mass of the desired products. And you can get that just from adding up the molar masses in a chemical equation, divided by the mass of all of the products, times 100. It's basically asking, overall, how wasteful is this process, just in terms of the masses. However, green chemistry goes a bit beyond that. So what if let's say I'm going A plus B reacts to form C plus D, where D is my desired product. So the atom economy might be quite good in this, but what happens if C is super nasty? What happens if we need a particular solvent that's carcinogenic? What if we need super, super high temperatures? What if we need a catalyst here that's awful? So green chemistry actually encourages us to look beyond, and I'm just switching to my laser. Green chemistry encourages us to look beyond atom economy and start looking at, is there a way I can do this without this solvent? Is there a way I can do it where I'm not making that super nasty product? Is there a way I can do it at lower temperatures or with a different catalyst? That's what green chemistry is asking us to do, to look at that wider environmental impact rather than just what is effectively a yield calculation. Okay, so let's look at this. I described what a xenobiotic was. I talked about compostable or biodegradable plastics. I talked about host-guest chemistry, and I compared it to enzymes. I talked about how we use enzymes to break down oil spills and other waste. I talked about enzymes in biological detergents. I talked about biomagnification, and I discussed green chemistry as an approach to chemical research. So I discussed the issues with human uses of something like antibiotics and how that's an issue. I talked about the role of starch in plastics. I didn't talk about this. I will find an example and discuss that another time. I discussed an example of biomagnification, talking about DDT. And I talked about how we assess a greenness. You don't need to know the specific names of green chemicals, and explanations of host-gas chemistry should... Sorry, I'm not quite sure what happened there. I think I clicked something which changed something. So emphasis on explanation should be on the non-covalent bonding. Okay, so other than talking about host-gas chemistry to remove a specific pollutant, I feel I've covered this. I will get an example of host-gas chemistry and I will talk about that in our video chat. Thank you so much. Have a fantastic rest of your day and I'll see you next time. Bye.